Okay, so, oh right, you have to take the quiz first. Go ahead and take the quiz. All right, let's go over the quiz. Using an integrating factor is another way to solve what kind of differential equation? Linear.
I said non-homogeneous.
No, it has to be linear. It does not have to be non-homogeneous. It can be homogeneous or non-homogeneous. Mu of t equals e to the integral of g of t dt. What is that thing called? Integrating factor. True or false, the method of integrating factors requires a guess for mu of t. False. Right, so the method we learned last class involved the guessing technique for solving linear differential equations. Today's method doesn't require any guessing. Okay, so to find an explicit solution to a linear differential equation that has the form dy dt plus g of t times y equals b of t, you can first compute an integrating factor. Okay, so remember, g of t and b of t just means some stuff with t's in it. So this is linear because the y is y to the first. Right? So that's why this is a linear equation. All right, so the integrating factor is called mu of t. It's e to the integral of g of t dt. You only need one integrating factor, so when you're calculating the integral of g of t dt, take the most convenient choice for the arbitrary constant, the plus c at the end, or if it's an exponential, there's a c in front, right? So just pick the easiest one, 0 or 1, make it the simplest possible. All right, so once you have calculated mu of t, you can determine the solutions by multiplying both sides of your differential equation by mu of t, and you'll see something that you should be able to recognize as the result of the product rule. And then once you have seen that, integrating both sides is pretty easy. Okay. So choosing mu of t to be that e to the integral of g of t dt, it guarantees that you're always going to see the product rule, which makes the integration step easy. So that's why mu of t is what it is. It's guaranteeing that the product rule will pop up in our result. All right, so for example, I want to find a general solution to dy dt plus 3y equals t. So step 1 is to calculate the integrating factor, mu of t. This is e to the integral. In this case, what's g of t?
3y.
Just 3. It's just the coefficient on it. It's just the stuff with the t's. Yeah, so it's just 3 dt. 3 dt. All right, what is the integral of 3 dt?
3t.
It's 3t. Technically, it's 3t plus c, but you choose the easiest c possible because we only need one integrating factor. So this becomes e to the 3t. So we now have an integrating factor. So I'm going to rewrite my differential equation, dy dt plus 3y equals t, and I multiply both sides of the equation by e to the 3t. Okay, so my right-hand side becomes t e to the 3t. My left-hand side, I'm going to distribute that e to the 3t. So I have e to the 3t dy dt plus 3y e to the 3t. Now, this we should be able to recognize as the result of applying the product rule. So this is a function e to the 3t times the derivative of another function, right? So this is like first times the derivative of the second plus the second, y is all by itself, right? Just regular old y. And 3e to the 3t is the derivative of e to the 3t. So this is the derivative. This is the derivative of y times e to the 3t. If I applied the product rule to y times e to the 3t, I would get this. Everybody sees that? So that's like the key. And you'll always, at this step, see the product rule. Okay? Anytime you're using integrating factors, this is the key step. It's to look at the left-hand side of that thing and say, okay, what functions did I apply the product rule to get this? Okay, the right-hand side just stays t e to the 3t. Now, my next step is to integrate both sides. Next step is just to integrate both sides. So the fact that I have the product rule on the left makes the left side easy. Okay, so I'm just going to do integrate, integrate. Now the integral of a derivative is just the thing. They undo each other, right? So this becomes y times e to the 3t. Now, the right-hand side, how do you integrate t e to the 3t? What's the analogous thing for the product rule when you're taking an antiderivative? Product rule is to take a derivative. Integration by parts. U and dv, yeah. So let me I'm just going to leave this. I'm just going to go to another slide and we'll review how to do by parts on this. Yeah.
Could you do something? No.
No, U substitution is not going to work.
No, because
U
the t
v.
will disappear.
Because you
If
do
it was t squared at the top.
If there was a t squared in the exponent, yeah, it would work. But with just the t, it won't work. Not everything will cancel. All right, so let's go back. I want to integrate t e to the 3t dt by parts, right? So I have to pick a u and a dv.
Let's pick T or U.
Make t or u. That's a good choice.
DU is
And so then dv would be e to the 3t dt. Right? So what made you choose u to be t and dv to be e to the 3t?
Simplest terms, it's really easy to take the antiderivative of e to the 3t, and it's easy
Yeah.
to take the derivative of t.
Well, it would be easy to switch it too, right? It's easy to take the antiderivative of t and the derivative of e to the 3t.
Right.
So why did you choose this way?
Take the derivative of t disappears.
Oh, yes. When you take the derivative of t, the t disappears. That's a good thing, right? You kind of got rid of a variable. And as a general rule of thumb, you want to pick the more complicated thing to be dv, so long as it's possible to get its antiderivative. All right, so when I take du here, I get dt, and then integrate both sides of this one, and you get v is 1/3 e to the 3t. And then integration by parts, if you remember, it said if you're trying to take the integral of u times dv, that's equal to u times v minus the integral of v du.
I hate how they use,
I said spark.
I hate how they use V's and U's because when I write them down, they look the same.
Put a little thing on your.
All right, so u times v, this becomes 1/3 t e to the 3t minus the integral of v times du, so that's just v dt. So I have 1/3 e to the 3t dt. So just plugging into my formula, u times v minus integral of v du. So the whole idea of using by parts is that it takes a complicated looking integral and it breaks it down. You still have an integral left, but now it's easier. It's an easier integral to evaluate.
Yeah.
So I'm almost done. This part I'm just going to copy. 1/3 t e to the 3t minus 1/3. I'm just going to pull that out of the integral. And then what's the antiderivative of e to the 3t?
It's e to the 3t, right?
Close.
1/3.
1/3 e to the 3t. So this actually becomes a 1/9. 1/9 e to the 3t plus c.
Is it possible?
Let's see.
Plus C, yep.
Minus 50 on final grade. You did get it.
All right, everybody like kind of remember how to do integration by parts?
Yeah.
Okay.
Yeah, because you had the limitation for.
So the right-hand side of your equation is not always going to require integration by parts, but you do have to integrate the right-hand side, and you might require a variety of integration techniques. Okay. This is one that comes up a lot.
That's what I was trying to say.
All right, so I'm going to take this guy and put it back in the line I was just working on. Right, so go back to the previous slide. 1/3 t e to the 3t. 1/3 t e to the 3t, and then the next part was minus 1/9 e to the 3t. Oops. Minus 1/9 e to the 3t plus c.
Also, all we do is make one dominated.
So what am I trying to get here? What's my goal? What?
I don't know what the goal is.
Y by itself.
Yeah, well, y by itself, right? The solution to a differential equation, dy dt with some stuff in y's and t's, the solution is a function y, right? So this very last step here is I would like to get y by itself, which is divide both sides by e to the 3t.
So can you also solve this the methods from last class?
Yes, you can also do this using the method we learned last class.
So if you want. So
As soon as we can.
well, how do you do this? Oh, okay.
So it's very elegant.
You can just. Plus C.
Sorry, no, I need to divide by e to c over e to the 3t.
Yeah, but isn't that
just.
isn't C still arbitrary?
Yeah, C is still arbitrary.
C is still arbitrary, yes.
So why does
Why can't
the
we? It's just C.
Because there's a T in there.
We could, yes.
So it can't.
Yeah, it's not like c over 5. Right, there's a variable in there.
And it doesn't.
okay.
I would argue that.
I'm giving you a take-home quiz today. I think it's the last question on the quiz asks you to solve a linear differential equation. I did not tell you what method to use. So like you mentioned, Alex, you can use the method we learned last class, the 3-step method that involves a lucky guess, or you can use the method we just learned. All right, let's look at another mixture problem. Right, we had the one with the sugar mixture for soda earlier in the semester. We're going to look at a pond that has an initial volume of 10,000 cubic meters. Suppose that at time 0, the water in the pond is clean, and that the pond has 2 streams flowing into it and 1 stream flowing out. 500 cubic meters of water per day flow into the pond from stream A. So 500 cubic meters per day go in through A, and 750 flow in through B. 750 cubic meters per day, right? And then 1,250 cubic meters flow out of the pond, which is the sum of 500 and 750. So the amount of water in the pond is always constant. 1,250 cubic meters per day flow out. Okay, so at time 0, the water flowing into the pond from stream A becomes contaminated with road salt at a concentration of 5 kilograms per 1,000 cubic meters. And let's just suppose the water in the pond is well mixed, so the concentration of salt at any given time is constant. And to make matters worse, at time 0, someone begins dumping trash into the actual pond, not into one of the rivers, but they are dumping trash into the pond at a rate of 50 cubic meters per day. The trash settles to the bottom of the pond, reducing the volume of the pond by 50 cubic meters per day.
That's a lot of trash.
It is a lot of trash, yeah.
So wouldn't that increase the flow out?
Yep. So that's the last sentence. To adjust for the incoming trash, the rate that water flows out via stream C is going to increase to 1,300 cubic meters per day.
Disgusting.
Okay, so that the banks of the pond don't overflow. So I would like to write a model for S of t the amount of salt in the pond at time t. So S of t is the amount of salt in the pond. So let's just write that down. Of salt in the pond, and we're going to measure that in kilograms, right? Because that's how they're measuring salt here. Yeah, because you're using kilograms to measure salt. Okay, so I have to write a differential equation that models the amount of salt here. So I know about how the amount of salt is changing, so I'm going to write an equation ds dt. So how the amount of salt is changing, and that some salt is entering, right? So I'm going to do the rate salt enters the pond minus the rate salt leaves the pond. All right, how fast is salt entering the pond?
5 kilograms per 1,000 cubic meters.
Okay, 5 kilograms per 1,000 cubic meters, but ds dt, that should be kilograms per, what's my unit on t here? Time or days, yeah. So I need to know how many kilograms per day are going into the pond. 2.5 or 5 over 2. Good. Let me write it out on the next page how we get that. So the rate salt enters. Well, we know that water enters at 500 cubic meters per day. 500 cubic meters per day. And the salt has a concentration of 5 kilograms per 1,000 cubic meters. That's what was given. And then your cubic meters cancel, so you get kilograms per day. 500 times 5 over 1,000 is 2.5 kilograms per day. So we'll go back to my differential equation, and I have ds dt. Salt is entering at 2.5 kilograms per day. Then I have to figure out the rate at which salt is leaving. So let's do that as a little aside over here too. Rate salt leaves. All right, so I'm starting with the water speed like I did before. It's 1,300 cubic meters per day.
That's the rate.
That's the rate that water leaves.
Okay.
That's the rate that water leaves out of the pond. And then I need to know how much salt, the concentration of the salt. Here it was 5 kilograms per 1,000 cubic meters. Not quite as obvious here because the amount of salt in the pond is changing, right? How much salt is in the pond? S kilograms, right? So we have S on top here because it's changing with time, right? And then my denominator has to be an amount of water, right? How much water is in the pond? It was 10,000, but then what's happening with the whole trash thing? Yeah, the volume of the pond is actually decreasing by 50 cubic meters per day. So it started at 10,000, but we're losing 50 cubic meters per day. This is my concentration of salt in the pond that's flowing out via River C. This is cubic meters. This is kilograms. Cubic meters cancels. So this simplifies. You can verify this for me on your own to 26S over 200 minus T. Just simplifying the fraction, right?
We'll see about that.
It's 1300 S over 10,000 minus 50 T.
It's just 1,300.
Just
divided
reduce
by
the fraction.
50.
Yeah. All right, so the rate salt is leaving is 26 S over 200 minus T. So I come over here and I put that here. 26 S over 200 minus T. All right, and then do I have an initial value? How much salt is in the pond at time 0?
Yeah.
None, right? The pond was clean at the beginning, they told us. So my initial value is that S of 0 is 0. So this is my model for how the amount of salt in the pond is changing.
It's a salt water. Whatever it was.
All right, in the class activities, I'm going to ask you to solve that initial value problem using an integrating factor. But for now, I'm just going to look at its slope field, and we're going to sketch a solution for the initial value. All right, so our initial value is that S of 0 was 0, so that's here. And then we have to just kind of try to follow the slope field, and it looks like it's really steep at first, and then it kind of goes down like this. Right, and this is time, and this is S for kilograms of salt in the pond. Okay, so that's my solution. Does that make sense?
Yeah.
What is it saying about the amount of salt in the pond?
It's going to go down because the
Yeah.
space in the pond.
Oh,
is
yeah,
increased.
because the pond's not going to 0.
Yeah.
Yeah. At first, that,
Right.
that makes no sense, but then the pond itself.
At
goes
first,
0.
there's a lot of salt being put into this pond, right? But then, like you said, the trash is starting to take up more and more room, so there's actually no water in the pond at the end, which means that there can't be any salt in the pond either.
Well, are we factoring in that most trash bags are round? Well, if they're trash bags are round.
Oh, so like water could fit in between, yeah. No, I don't think we're taking that into account.
Style. Yeah, borax. Crunching it for a square.
All right, so that's it for the lecture part. You guys are going to start on your activities,
Yeah,
solving by
salt.
integrating factors.